Hello again, folks, in 114. Today we're going to be covering section 12.6, which for us is the last section, the very last. All right, today is Tuesday, June 29th, so section 12.6. Okay, and the packet consists of another hefty one. There's this overview about modeling, and I'll go through this in intricate detail in a moment, but print this out if you will and we'll annotate. I was debating going through another vocabulary list like this, but I did include that for you if you want. Then this is a worksheet that will basically describe how to basically perform this calculation, just to do it maybe one time. Mostly you're going to use your calculator. Then there's another diagram about level of significance. All right, and I broke up, there's a table I swiped from your textbook that I just sort of like cut and pasted in pieces all around it, so you don't have to go hunting for it. And then there's a graph to illustrate one example. Okay. And then there's the actual diagrams that I swiped from the textbook. This includes the definitions. Okay. And this is especially useful. All right. There's a smaller copy of this on one of my own diagrams, just to see, briefly what I'm referring to. But if you want detail, I would definitely print this out because this is a very nice summary of scatter plots. And there's also a nicer view of this these critical values for level of significance. All right, and then there's the actual formulas for calculating the slope and the y-intercept of a line at best fit. Right. You will realistically be doing this with your calculator, so at this point you absolutely definitely want this. All right, have that ready. And then there's some examples that we'll go through here. I think there's 4 of them. Yes, okay. And I'll just go through the details of each. Okay, so if you find it useful, print this stuff out, and we'll continue. I'm going to adjust the lights here. It's 90-something degrees today. Let's see how far we can get before I keel over. I promise not to faint on camera. Okay. All right. I think I will, just to be on the safe side, go through the vocabulary first, and then go through the diagrams, which explains much of the same information, but I think it's better to reinforce. Let's see. All right, now I gotta adjust this. Some light. Very good. Oh, wow. Okay, so again, here's our overview where we have been. All right, we're in chapter 12, basic statistics. All right, gathering data, presenting it in the form of some graph. Measures of central tendency, otherwise known as types of averages, types of position. These were section 12.1, 2, and 3 respectively. This is section 12.4, types of variation, including standard deviation. And the last thing that we did was types of distribution graphs, right, where we broached the subject of normal or Gaussian distribution. We are here at the finish line, or nearly, section 12.6, modeling. All right, basically writing formulas for the sake of predicting data that is beyond the scope of the that we have to work with. All right, so basically you look for a pattern right, from the data that you have, and you write an equation so that you will not need any additional data. You can make predictions from the mathematical model. All right. The type of regression that we'll be doing is just simply linear regression, which is y equals mx plus b, basically the equation of a line. Again, not to be dry, but humor me a moment. I want to get through some vocabulary to make sure that I cover it all. And again, my diagrams will basically reinforce this. But let's make sure that we're super clear on what needs to be discussed here. Okay. What am I going to do? I'll try to summarize. And hopefully choose markers that write nicely. See how bad luck with that. Okay. Basically, we're going to be discussing correlation and regression. That's a good one. And maybe the temperature helps. These are writing very smooth today. And then we'll be interested in what is referred to as a linear correlation coefficient. Okay. Eventually we're going to get into the subject of levels of significance. Not too faint. Let me just turn around and check the camera here. Looks like it's okay, right? Line of best fit, which has a lot of alternative names. And this phrase, bivariate data. Alright, so there's a lot of terminology to acquaint with. Okay. Correlation, there is no symbol for this. Let me get my mouse out of the way. It is the process of determining whether there is a relationship, or rather if there is a relationship between variables and if so, how strong? How strong? Okay. Regression is essentially the process of determining an equation to describe that relationship. As for the linear correlation coefficient, this is a way. It's symbolized by the letter R, lowercase r. This basically describes the strength of the relationship. Essentially for right now, you'll see a graph in a moment. 0 equals no relationship. 1 plus or minus equals strong relationship. Hopefully this will right. Level of significance is symbolized by the Greek alpha. It's a little faint, right? This is used to describe a cutoff point. Is that visible? I think it's a little faint. A cutoff limit of results due to chance only, rather than having a genuine relationship. The line of best fit is essentially going to be y equals mx plus b. The only difference now is that the labels might change. So if you use your calculator again, and you really would want to, it would spare you a lot of trouble. In your calculator, after you've entered the data and you tell it to give you the line of best fit, it'll give you something labeled A and B, right? B is still the y-intercept. A is standing in place of the slope. This is a line such that the vertical distance from any data point to the line is minimal. It's more or less an ideal. When you'll see data that has been measured. Because it's been measured, it's never going to be perfect, really. Right? So it'll appear in the form of what is referred to as a scatter plot, which looks like maybe a pattern of dots that is relatively close together, but not really collinear. Anyhow, we use that data to basically construct an equation in the form of a line equation for our purposes that ideally is right in the middle of it, a perfect middle, if you will. All right? A line such that the vertical distance from any data point to the line is minimal. Right? Used to best describe. All right? Bivariate data, as I'm short on space, is going to be maybe symbolized as something like this. All right. Because I'm short on space, I'll just tell you. It's a data set involving two variables. Blue is dying. Okay. That's that. There you go, blue. All right. So just to summarize, correlation is the process of determining if there is a relationship between variables. Usually it's two, and for our cases it's only two. All right, and how strong? Regression is the process of determining the actual equation to describe that relationship. A linear correlation coefficient describes the strength of the relationship. It's more or less a ratio. This is a ratio, which means it's a glorified fraction. Right. And you'll be comparing whatever figure you get to a scale of negative to positive 1. Right? If you have 0, we say that there's no relationship. If you have either something right on top of 1 or negative 1, then there's a strong relationship. It might be a negative sloping graph or a positive sloping graph. Level of significance is abbreviated by alpha, and it's used to describe a cutoff limit of results due to chance only. Mere chance, not really a genuine relationship, right? The line of best fit is, again, y equals mx plus b, just maybe disguised with a different label. All right, a line such that the vertical distance from any data point to the line is minimal, and bivariate data is essentially a data set involving two variables, right? X and Y for all intents and purposes. All right, for simplicity's sake, I should say. Okay, now, that's pretty much all of the terminology that you will see. All right, let me explain this diagram to summarize what we'll be doing largely here. Okay, the point of all of this is modeling. And modeling is a way of predicting the future, using math to predict the future. We take a pattern and we try to establish a mathematical equation to describe that pattern, and then we can extrapolate. Right? Or interpolate if necessary. Extrapolating is basically predicting a data point beyond what you have to start with, and interpolating is predicting a data point that would be in between the data that you have. Okay, anyhow, correlation for will be two variable relationships, right, is again the process used to determine is there a relationship, right? And how will we decide that? Well, we look at plots of data, right? This is a smaller picture of that sheet which you have available in the packet. Again, I really want to encourage you to print that because it's very useful. So basically this page, right, this is swiped from your textbook, but it summarizes this information, right? It's no difficulty, right, to take some points and graph them on a two-dimensional coordinate plane, right? But they sometimes form a nice pattern and sometimes less and less, all right? And as you can see, all right, using a linear coefficient, linear correlation coefficient here, R, it may either have a nice perfect relationship, which would be strong 1 here, or maybe a strong negative slope, right? Or a little bit less than that. Right? And then diminishing to the point where there's really no relationship. If you just have a square pattern of dots, there's probably no relationship between your two variables. All right, anyhow, so we look for a relationship and we decide that based upon how things look. All right, graph your points, you see something weird like this, there's probably no relationship. All right, you see something like this, all right, then well, this for sure, all right, but these other two situations, maybe. Okay. To quantify, how strong is the relationship, we calculate a correlation coefficient known as R, and we compare it on this scale here. As you can see, again, I swiped this diagram from the same packet. All right. If there is no relationship, right, then you're probably at 0 or close to it. All right. If there's a strong relationship, it would either be a magnitude of 1, right, negative or positive. Right? Don't be deterred by seeing a negative. It just means that the data is sloping. right? In a downward position from left to right. Okay. Now, let me just show you too. This is the formula, all right, for determining the linear correlation coefficient, and as you can see, it's quite complex. All right, there's a lot of steps here. All right, but in its most basic form, all right, there's a line here, right? You see this line that separates the top and the bottom, which means that once you boil it down to a number on top and a number on the bottom, what is it? It's a glorified fraction. All right. So that's why you're comparing things sort of inversely proportional. All right. 0 is not a good relationship, but there's no correlation. All right. But if you have, the maximum would be 1, right, when you have a fraction, right, ideally. Unless it's improper, but that's another story. You're not going to get an improper fraction. Normally you will have a fraction that is some figure that is a half, a quarter, 3/4, something like that in this realm or here. Right? Just don't ever be bogged down by the complexity of your formula. All right? Just look for what is familiar. All right? All right? This is ugly, perhaps. All right? And I'm going to show you how to do the calculation by hand just one time. But you're going to use your calculator anyway. All right? It's really just a fraction, right? It's just a complex fraction. So one number boiled down to on top and one number on the bottom. Okay. Now the other side here, regression. All right. Remember, that's basically the equation to describe it. If a linear relationship, because that's what we're doing, exists, all right, then we will try to produce a regression line. All right. Otherwise known as the line of least squares. Line of least squares. There's 3 names to describe the same thing, all right? Line of best fit probably gets at the feel for what we're doing better than anything, but you may alternatively hear of it as this least squares line or this regression line, all right? And this is the model that we have from, algebra, right? Y equals mx plus b. We know that there are jobs, basically, for these 2 parts, the slope and the y-intercept. Let me scoot this up just a little bit. Okay. All right. There's a formula for calculating this, again, brute force by hand if necessary. Realistically, again, you're going to use a calculator to do that. And there's a second formula for calculating the slope. Also rather tedious, all right? Don't forget what do these things really describe in terms of an actual graph, all right? Since we're dealing with real life, all right, and not math world, usually we're just limited to the scope of quadrant 1, all right, rather than quadrant 2, 3, and 4, all right? Which essentially makes this point here, the slope, a starting point of the line, all right? Pardon me, the y-intercept is the starting point of the line. You can see here I put it in green. Here's just some data points, and here's the ideal line that is, minimally distant from here vertically, here vertically, here vertically, here vertically, and so forth. All right, it's right smack in the middle, essentially. All right, if you were truly, short for time, all right, and you wanted to create a line of best fit, you could eyeball it, right? I think that is what people used to do a lot in the old days. But if you want to get something, chef's kiss, as best, blessed as you possibly can, all right, then indeed you would run some calculations. All right, here's the formulas again, not to intimidate you. This is a very similar looking equation to regression coefficient, right? It is a glorified fraction. A lot of stuff to do on top, a lot of stuff to do on bottom, but in the end it's just a fraction, right? Similarly over here, all right? Anyhow, think of the slope as the unit conversion factor, all right? Whatever units your first variable is, all right? Whatever your units your other variable is, all right? The slope involves both of them technically, and it converts the independent variable into a dependent variable. All right. A lot of times these, because you'll be dealing with data that describes some, an experiment or some real life situation, they will not simply refer to it as X and Y, but you could call it that if you want, right? Because it's warm, fuzzy, and familiar. More likely what you'll see is that they'll refer to the horizontal axis as the independent variable axis, right? And the y-axis as the dependent variable axis, right? Right? An input, if you want to stick with function speak, and an output. Right? As is often the case in math, there's more than one way to do something, and there's more than one way to talk about something. Right? So don't let it intimidate you. Okay, it's just y equals mx plus b. All right. Okay. And of course, slope does what? It determines the pitch of the line. So if you get a negative slope, it just means that it's pitched this way. Okay. Let me mention one other thing since I'm down here. If once you've calculated your R value, you end up with something that is in the negative realm here. All right. In terms of the variables, that basically means this. All right. As x increases, I'll put this as an upward pointing arrow. All right. Y would be decreasing. All right. If you are in the realm of a positive coefficient, then they're both increasing. As x increases, y also increases. Like that situation would be positive. All right. Let's do an example. Let's see. Looking at the examples packet here, we'll do these. We'll start this. Get rid of this view here. All right. Here's a graph of some data. And it's bivariate data, which just means it's two components. In order to graph in 2 dimensions, you need 2 variables, right? So just to summarize some information here. Bivariate, right, which means 2 variables essentially. Where's my blue not cooperating? It's the dud. Is that visible? Not really. Two variable data, which for all intents and purposes we can just think of as x and y, all right? Graph. And basically when you first basically tie 2 pieces of data together, a bunch of X's and a bunch of Y's, all right, you're hoping that there's a relationship. Hoping there's a legitimate relationship. You don't know. Okay. If they, now there's not a heck of a lot of data here, but there seems to be upward pointing in general, right? Yes, you could get a ruler and kind of cheat here and try to get a line of best fit by eyeballing it, right? And then you could use that line to predict a data point that is beyond the scope of the graph, extrapolate, or get some data point that is in between, interpolate, right? But that's not what we're after here, right? What we're after is calculating the correlation coefficient, because that will help us legitimize our assumption that there is a legitimate relationship. Egan Electronics provided the following daily records about the number of assembly line workers absent, right? Absentees, and the number of defective parts produced for 6 days. Okay. Determine the correlation coefficient between the number of workers absent and the number of defective parts. Now, because of the way that they have phrased this, absentees, basically, I want to put it in a place I don't have to move it. Absent workers versus number of defective parts, all right? Let's assume that this is the independent variable and this is the dependent variable. The defective parts is dependent upon people being absent. It's unfortunate because there's a third row here which might mislead you, all right? Yes, the data was taken over the course of 6 days, all right? But the increments that you see here are not the days, all right? The increments that you see here are the number of absentee workers, all right? So this is absentees, all right? 6 absentees, 5, 4, 3, 2, 1. Just put in numerical order, all right? All right, that's X basically. And the number of defective parts is Y, right? Which means these two paired together are an ordered pair, X and Y. These are an X and Y. These are an X and Y. These are an X and Y, and so forth, right? This is just more or less a label that coincides, right? It's not these figures along the bottom, okay? Now, the simplest thing to do is to take this information and plug it into your calculator, so I'll do that first. Right. Here. Right. Now, in order to do that, you have to clear out whatever old SCSI data is in there. All right. So turn on your calculator. You don't have to have logarithms in. Hit second and then data. And you'll see that there is, we had been working in one variable statistics. We're eventually going to choose 2 variable, but before I get there, I want to make sure that we clear out any old data. All right. All right, now you could assume that that is clear. All right, if you hit data now, it'd be empty. All right. I'm doing it backwards, so it doesn't help me. All right. Now we're going to choose 2 variable statistics because we're working with 2 variables. Right? If you need to, scroll over to underline it, hit enter, and now when you press data, you're going to see X1, and then as you scroll down, Y1. Okay, so put in these things that you see, 350126 as the X's, and these things 15, 22, 7, 12, 20, and 30 as the Y's. All right. Be careful as you're doing it because you don't want to accidentally conflate one with the other or switch them. Here, give me while I do it, and then I'll show you what the result was. Okay. Here I am down at the bottom So the sixth data point is a subscript of 6. All right, that's 30. I'll point to you with my other finger. 36, 22, 12, 1, 7, 0 for x, 22, 2. That's a 5, rather. Yes. Okay. And 15, 3. All right. Now that is inputted into your calculator, you'll hit stat var, and it will give you some of the same information that you're familiar with already. It will tell you that there's 6 data points, but they're data points paired together, right? It's bivariate, right? So even though I put in technically 12, right? 2, 4, 6, 8, 10, 12 things, right? They're a pair, so there is essentially 6 data points. Okay, you could calculate an average, I suppose. All right, of which I'm not sure. I guess if it's just the x's, then that's just the x's. All right, here are the standard deviations. Here's the average of the y's. All right, what we're really after is hanging out on the end here, which is this r value. All right, these a and b that you see here, those are the slope and y-intercept respectively. All right, but we're not really after that right now. Here is the linear correlation coefficient. All right, 0.95, whatever it is, or 0.92. If you round it, 922. All right. So the R value, right, the correlation coefficient is R about equal to 0.922 if you round it. All right. If the scale, and it's a positive notice, if the scale is from +1 to -1 and 0 is right in between, and 0 means that there's no relationship, and either 1 in this direction or 1 in this direction is strong, one would assume how close that this is to +1, that this is a strong relationship, meaning that it's a very good assumption that you'll have more defective parts, all right, if you have more people who are absent from work. Okay. And notice also, just to complete this thought, right, you could kind of tell from the graph, without drawing a line, that this tends to be pitching upward from left to right, which means as x is increasing this way, y also is increasing this way. Right? A positive linear correlation coefficient implies that as well without the graph. Now, I'm thinking it might be silly, so let me minimize this a minute. This is a sheet, all right, with the linear correlation coefficient formula, and columns of prepared for taking this data and calculating this brute force. All right. I don't think I'm going to go through that because it is kind of silly, especially if you have a calculator to do this for you. All right. But were you going to do this by hand? That is calculate 0.922. This is how you would have to go about the process. You would have to calculate a lot of sums, you'll see here. Think of this as, a term, product, and another term that is 2 products of sums. Remember, sigma is a sum, which means you have to add things. You would have to construct a table, something like this, all right, and write your data values 3, 5, 0, 1, 2, 6. You know, write your y values, you know, the half of the ordered pairs, 15, 22, 7, 12, and so forth. And then systematically square the x's, square the y's, multiply them together. All right, and then maybe totals them. All right. All right, and then follow the order of operations. It would be rather tedious, so I guess I won't do that. All right. For the sake of expediency, I'll skip that. Anyhow, you will get the same figure, 0.922 roughly. All right, let's discuss levels of significance now, which is this diagram I prepared here. All right, as I stated, I meant to imply, ignore the boxes here and here for a moment. I just included them because it would be practical to have the information all on one page, not to get you distracted. All right, just look at my diagram, that is the bubbles here. Level of significance is abbreviated by, or signified by, a lowercase alpha. All right, and it's used essentially to identify the limit, or basically a cutoff, between results attributable to chance, that is, they're merely coincidental, and those with an actual genuine relationship between them. Right? Now, once you have calculated alpha, or your linear, you use linear correlation coefficient R still, right? You're going to compare your R value, the absolute value of your R value, which means a positive no matter what. We're just looking at magnitude. If the magnitude of your correlation coefficient is greater than the alpha, all right, that is the critical value at a specified sample size, all right, either for 5% or 1% chance unrelated, all right, they're column headings you'll see, then you assume that there is a relationship, all right, a genuine relationship, all right. If you have a correlation coefficient magnitude that is less than, this is greater, this is less, then again, the critical value, which is a decimal number, at a specified sample size, maybe you had 6 points of data, maybe you had more, for either 5% or 1% chance unrelated, then you assume that the correlation does not exist. Right? This is another way to help substantiate a relationship. Right? Essentially, the larger the sample size, the smaller the value of R needed, necessary, to certify a relationship. Right? This is often the case. Right? More data is more trustworthy. Right? What does that mean? Well, if you look at the actual tables now, right, you'll see a column heading for alpha that is 0.05, and then an adjacent column heading that is alpha 0.01, right? This is a 1% chance of uncertainty. This is a 5% chance. Pardon me. Think of this as being 1% unrelated, 5% unrelated. All right. The n value that you see here is the number of data values, the sample size. So that's 4 data values, 4 points, all right, 5 points, 6 points, all right. And as you scroll down this, if you notice that the critical value is for alpha is smaller and smaller and smaller, all right, because more data is more trustworthy, all right. The way that I broke it up is that it cuts off at 13 here, and the rest of it is further down the page. Okay. So here you have 0.532, you know, and then it diminishes into 4.4. All right, again, still for the same column headings, 5% level of significance, 1%. Okay? And then the rest of it is on the other side. You don't have to look at this. You can, if you dig through the same packet, there's a page that has the whole thing in one shot. Yeah, I turned it sideways in this case, but here's the same table. Okay. All right. Let's go back to the examples here. That's the brute force calculation. Okay. All right. Let me just, because we bothered to calculate the linear correlation coefficient from earlier. Let me show you something really quick. Using bootleg paint for a moment here. All right. Okay. All right, we look over at this corner here again, 5% or 1% level of significance. We had calculated the R value from example 1. That's too faint. We had calculated example 1's R value as being about 0.922. And it was in fact positive, but we had 6 points of data, so we could either read it at 5% level of significance or 1% level of significance here. All right. If I take this R value and slip it into some absolute value lines, we'll decide what the relationship is to alpha at firstly 5%, 0.811, and then at 1%, 0.917. Okay. The absolute value of 0.922 is going to be 0.922, nonetheless. All right. And as you can see in both instances, all right, 0.92 is greater than 0.81 or 0.91 in both cases. All right. This R linear correlation coefficient is greater than this critical value, and it is still greater than this secondary critical value, which is a little bit more strict. All right, stringent. All right. So what does that mean? It means we can further assume, all right, that a correlation exists. All right, it's reasonable. All right, it's not mere coincidence. Okay. Now let's do. Another here. Alright, look at example 3 now. for example 3, we're going to use the data from example 1, all right, to find the equation of a line of best fit that relates the number of workers absent on an assembly line and the number of defective parts produced. All right. Then we would graph the equation of the line of best fit on a scatter diagram that illustrates the set of bivariate points. Okay. Now I kind of did this already anyhow, so let's complete this thought. All right. If this is our model, all right, data from example 1, we need 2 voids to fill in here in the model. All right, we need the slope and we need the y-intercept. And your calculator, this is called A and this is still called B. All right. In some textbooks they might call this B naught and B subscript 1, but it doesn't matter. Anyhow, let me go back to this. I didn't erase anything. I'll turn it on. And then we'll just scroll over to where it says A and B respectively. All right, here's the slope disguised essentially. 3.5 it looks like, or 3.2. 3.22. Is it rounding here? We'll just go with 3.2 for the sake of simplicity. And if you scroll over to adjacent B value, here's the y-intercept, 8.5. So without having to torture ourselves with the calculation, I'll write this a little bit nicer, a little bit neater. Here, this is y equals, this green hopefully will cooperate, 3.2 roughly x. See if that's the land there, just a little bit. Plus 8.5. Right. If I go back, I could try to superimpose it, but what would probably be practical is to help us with generating some extra points. Let me minimize this for a moment, and I'm going to pull up my bootleg Microsoft Paint here, just because it's a white surface. Alright. We, from this information, have a positive slope, and we have a starting point. On the graph. Right. Which is really enough information to graph it if we had to. But to make it a little bit easier, the argument is that, well, you know, why don't we get some of the points that are in between? Let's look what was missing for a moment. If you go back to example 1 for a moment, here's the data set. Whether you stare at this graph or you look at the actual rows of x and y's, you'll notice that there is some points here that are maybe we could fill in. There's no value for 4, so we could try to calculate that for 4. There is actually a value for 2, but since the line is probably going to be somewhere in between anyhow, let's do a value for 2, maybe for 4, and maybe for 6, right? Using this model, right, rather than eyeballing it. And I'll do the calculations here. Right. We're going to basically generate 3 additional points. Using this model. Okay, and we do that the old-fashioned way. Remember, we have an input, the actual function or the equation, and the work involved, and then we'll get an output, and then we could pair them together as ordered pairs, x and y. Okay, it's a little brute force, but it definitely is practical. All right, so let's just do 3 points. So let's say we use an x value of 2, 4, and 6, right? Because that's within the scope of the graph. Okay, and 4 was never even done to begin with. Okay, so if this is our equation, I'm going to write it purposely in green now because it's faint. 3.2 x plus 8.5. You could do 0 as well, actually. In fact, that's the ultimate in cheating, so maybe I'll do that. I'll use 0, right? That's easy. If I put 0 in place of x, all right, that's going to eliminate this term entirely, which means that your y value will just be the intercept of 8.5. Right? And therefore, we will have an ordered pair at 0, 8.5, 8.5. That's reasonable. If I did the same calculation now using x is 4, then I would substitute a 4 in here, and let's see, 3.2 times 4 is 8, 12.8, 12.8 added to 8.5 is 13, 11, 21. 21.3, which together is therefore at the location of 4, 21.3. And one more time for good measure here. If I substitute in place of x 6, then it's 6 times 3.2, 12, 19.2 plus 8.5, 7, 17, 27.7. Which again paired together is at the location of 6, just shy of 28. Now what I can do is go back to the graph, if there is one, and plot these 3 additional points. So here's the graph as it was. I'm going to have to clean up some gobbledygook here, just to make it less distracting. At 0, Here's 0. All right. It's a little hard to see because of the way that it's incremented, but exactly halfway between 5 and 10 would be 7.5, right? So 8.5 would be just a smidgen higher than this, perhaps. All right. Over here at 4, I'll use a little bit of help in here. We would have to go up to just a little bit more than 21. All right. So at the location of 4, I'm going to erase the construction line in a moment, but at the location of 4, I would have a dot that is just above 21. So maybe something like that. There. And then at 6, I'll go up to just shy of 28. Here's 25. Again, halfway between 25 and 30 would be 27.5, right? So just above that, almost halfway, a little bit more than halfway. I have a point here. Now let me erase this. And I'll try to get these 3 to cooperate. Hopefully this was going to write. That's pretty good. An arrow here. I can technically cut it off here. Y is equal to 3.2x plus 8.5. And as you can see, this line is in the middle between these scatter points. All right. I suppose somebody might argue like, why don't you just start with 5 because that was 0 to begin with. All right. Maybe I should have, but they still seem to align fairly well, which maybe is dumb luck. All right. Anyhow, do try to generate extra points. All right. To get the line of best fit, at least visually here. All right. This is the actual equation here. It's rounded, unfortunately, because it has to be. Right? The equations are quite complex, as you can see. But we did it via calculator rather than by these equations. Okay? To spare us a little bit of trouble. Okay? All right. Let's see. Let's take a look at 4. Oh, we have to go back to example 2. Alright, let's take a look at example 2 now, and then we'll do example 4 because they're dependent upon each other. Okay. Here's example 2. To test the length of time that an infection-fighting drug stays in a person's bloodstream, the doctor gives 300 milligrams of the drug to 10 people, all right, labeled 1 through 10 in the table below. Okay. Again, the shading is not the best choice here, whoever decided this, but the way that this is labeled, right? Once each hour for 10 hours, one of the 10 patients is selected at random, right? And that person's blood is tested to determine the amount of drug concentrated remaining in the bloodstream. The results are as follows, right? Don't pay attention to these. These are just that there's 10 points, right? More or less patients. All right, it's randomly a person. All right. Time is the independent variable x. All right. It's assumed that the amount of drug is dependent upon time. So this is your x value and this is your y value. All right, determine a level of significance of 5% whether a correlation exists, all right, between the time elapsed and the amount of drug remaining. All right. Well, we need to get the r value in order to answer this firstly. All right. So let's again pair these together as x's and y's. We're going to have to input these into our calculator to spare us the trouble of having to run the calculation by hand that many times, which is rather tedious. All right, so back to here. Turn on your calculator. Again, we're going to clear out what was there. All right, now when we go back to, make sure that this is again in 2 variable statistics as it is. Now when you press data, there should be a place for x and a place for y. Alright, and there is, good. Alright, so systematically take these values here and pair them together as bivariate data points. Okay, I'm going to do that just out of view here for a moment because it's easy to not do it backwards. 1 and then it's 250. Alright, 2 and then 230. Alright, 3 and then 200. 4 and then 210, 5 and then 140, 6 and then 120, 7 and then 210, 8 and then it looks like 100, 9 and then 90, and 10 and 85, and you can see it's trending down, even if it isn't perfect. Remember, you're doing this for random people, not just one person. All right, now just to scroll through this to make sure that it's all correct. Here's as it is inputted in my calculator here. 1 and 250, 2 and 230, 3 and 200, 4 and 210, 5 and 140, 6 and 120, 7 and 210, 8 and 100, 9 and 90, and 10 and 85. Okay, now that we have done that, if you hit stat var and scroll over to the very far end here, we'll get the linear correlation coefficient, which is negative in this case. Again, negative just simply means that it's sloping downward. So 0.87 looks like. let me write that up here. The linear correlation coefficient, this is from example 2, is about equal to negative 0.871 if you round it. Okay. All right. Now we need to look at the critical values for the sake of comparison. I think I have that written in here, so let me, we'll go to my diagram here. This is a nicer view of it. In the example, they wanted it, the level of significance at 5%. Okay. Now there's 10 points of data, so that is the sample size. What we need to do is, in looking at this, go to the sample size of 10 and look at the 5% level of significance here. Okay. If we take the absolute value of this, right, and then compare it to, at 5%, 0.632, you could say whether it's greater or less than. Okay. In this instance, all right, the absolute value of negative 0.871 is simply 0.871. Right? 0.871 of those, very hard to see. Is what? It is definitely greater than 0.632. Which means what? It means that there is a relationship. Okay? Here is, I hate to do this, but here's that reference. All right. If the linear correlation coefficient magnitude is greater than the critical value, the level of significance at 5% in this case, because that's what they asked for, and it is indeed greater, then we assume a correlation exists. Okay? Let's see. All right. Because it's a negative relationship on the scale, all right, here's 0, here's -1, here's +1. Our correlation coefficient is very close to -1. All right. What that is implying, even without the graph, is that as the x variable, the independent variable, increases, the dependent variable decreases. Right? We could see that if we had a scatter plot as well. All right, now to answer 4 here, it says determine the equation of a line of best fit between the time elapsed and the amount of drug remaining in a person's bloodstream. We already did the difficult, quote unquote, portion of this because we can put it into a calculator. All right. This is the data from example 2. All that means is that after we've gotten that correlation coefficient, is that we're going to scroll over to here where there's an A, and that is our slope. And notice that it is negative naturally. And then scroll over to here and get our y-intercept b. Okay. So if this is the model, y equals mx plus b, and we are basically filling in the void from the calculator's information here and here. Then what we have is this. Negative 18 point, if you really want to be precise, 0.9, so 0.9 repeating. All right. And for the slope, 263. Okay. Now, you could graph this if you really wanted to. The scale is a bit large, but the reason that it's so large is, of course, this represents a number of milligrams, right? So this is 263 milligrams, and therefore the slope, again, is a conversion factor. It's converting between time, cancels time, and then produces milligrams as an end result to add milligrams to milligrams. Right? It's a conversion factor. All right, now, if the average person is given 300 milligrams of the drug, how much will remain in the bloodstream after 5 hours? Okay. Really what we just need to do is input a 5 here. All right, so if y is equal to negative 18.09x, and x is time, plus 263, we're going to put 5 hours in here and then follow the order of operations. Right? Which means that what you should get is this. Y, that is the number of milligrams after 5 hours, 172.55 milligrams. All right, and that's basically it. All right. Get acquainted with your calculator. All right, it's pretty easy. It's just, it will spare you a lot of trouble in terms of doing the calculations by hand, which it's only more likely if you do that to make a mistake. All right, so you don't have to reinvent the wheel. You just need to know how to use your calculator appropriately. All right. I'm going to give you a couple of reminders here, and I'll turn this off. This is the very last section for the semester, the summer session, whichever you prefer to call it. For homework, actually, do section 12.6 in my lab. All right. Today is Tuesday, of course. Tomorrow, if you need to. All right. Do try to begin finishing up. If you haven't already. Any of my labs. All right. And we're done by Thursday. All right. On Thursday late evening. All right, all my labs are due. What I'm going to do is tomorrow, I'm going to basically email you a copy of the final. Okay. I want you to have, really for the reason, I want you to have a comprehensive study guide. If the whole point of this class is to prepare you for the praxis examination, well, insofar as MAT-114 is concerned, I'm going to give you, just to have it, this this final exam, and then I'll shoot a video likely tomorrow to explain the solutions. All right, what I want you to really do is focus on this. All right, you need to make sure that you get all your stuff done by Thursday. All right, late Thursday evening. Okay, and that is that. All right, thank you guys for sticking with me. I'll see you tomorrow. Be careful out there.